Introduction. You have probably met the trigonometric ratios cosine, sine, and tangent in a right-angled triangle and have used them to calculate the sides and angles of those triangles. We define the cosine, sine, and tangent as functions of all real numbers. These trigonometric functions are extremely important in science, engineering, and mathematics. Before we define the inverse trigonometric functions, we need to think about exactly what we mean by a function. A function f from a set of elements A to a set of elements B is a rule that assigns to each element x in A exactly one element f of x in B. Y is equal to sin x, y is equal to cos x, and y is equal to tan x are functions in the sense of this definition, with A and B being sets of real numbers. The symbols sin inverse x, cos inverse x, etc. for arc sin x, arc cos x, etc. were suggested by the astronomer Sir John F. W. Herschel, 1813. Now, come, let's learn about inverse trigonometric functions. Objectives. At the end of this lesson, you will be able to learn domain and range of trigonometric functions, explain graphs of trigonometric functions, learn properties of trigonometric functions, solve examples related to the inverse of trigonometric functions. Basic concepts. The inverse trigonometric functions are the inverse functions of the trigonometric functions. These are the inverse trigonometric functions. There's another notation for inverse trigonometric functions as given below. Cos inverse x is equal to arc cos x. Sin inverse x is equal to arc sin x. Tan inverse x is equal to arc tan x. Recall that if f is a one-to-one function with domain A and range B, then the inverse of f is the function denoted f inverse with domain B and range A, such that y is equal to f inverse of x if and only if x is equal to f of y. For a function to have an inverse, it must be one-to-one. Sometimes, when a function is not one-to-one, one can restrict its domain to make it one-to-one. For example, the function f of x is equal to x square with domain infinity infinity is not one-to-one. It does not pass the horizontal line test. However, if we restrict its domain to 0 infinity, it is one-to-one. It has an inverse. It is f inverse of x equal to square root of x. Because of their periodic nature, the trigonometric functions are not one-to-one. Graph of sine. Given a function, there are two ways to graph its inverse. First, take A, B points from f and plot them as B, A points on f inverse. Or, second, rotate the graph of f about the line y is equal to x. We will begin this discussion by finding the inverse of the sine function. This is the graph of f of x is equal to sin x. In order for a function f of x to have an inverse, its graph must be one-to-one. This can be verified by applying the horizontal line test, or HLT. A horizontal line intersects the graph at most once. Clearly, the graph of sin x fails this test. So, how do we define the inverse of sin x? Easily, we merely restrict the domain of sin x to the interval minus pi by 2 less than or equal to x less than or equal to pi by 2. On this interval, the graph does pass the HLT, yet keeps its full range -1, 1. Thus, sin inverse x or arc sin x exists. This is not the graph of sine inverse x. It is merely the part of the sin x function that is used to graph the inverse sine function. Let's now discuss some of the properties of arc sin x. First, sine inverse x or arc sin x reverses sin x. That is, if sin pi by 2 is equal to 1, then sine inverse 1 or arc sin 1 is equal to pi by 2. This is true for inverse functions in general. That is, if f of a is equal to b, then f inverse of b is equal to a. Similarly, since sin minus pi by 6 is equal to minus 1 by 2, then arc sin minus 1 by 2 is equal to minus pi by 6. Graph of inverse trigonometric functions. In this screen, we will learn about the graphs of the inverse trigonometric functions. Using this figure, the graph of arc sin x or sine inverse x can be easily obtained. The domain of sin x, that is, the set of inputs, is restricted to the interval minus pi by 2, pi by 2, and the range, that is, set of outputs, is minus 1, 1. For the inverse functions, these flip-flop. Therefore, we have for arc sin x, domain is equal to minus 1, 1 and range is equal to minus pi by 2, pi by 2. Remember that if a, b is a point on the graph of f, then b, a is a point on the graph of f inverse. This means that the graph of f inverse can be obtained by rotating the graph of f about the line y is equal to x. Using this idea of rotation and by plotting some points, we see this graph of arc sin x. The derivations of the graphs of arc cos x and arc tan x are similar to that of arc sin x. In both instances, intervals must be restricted. For arc cos x, we use the 1, minus 1 piece. On this restricted domain, arc cos x or cos inverse x exists. Domain and range. Look at this table now. It gives the inverse trigonometric function principal value branches along with their domains and ranges. Example. Find the principal value of tan inverse of minus square root 3. Solution. Let tan inverse of minus square root 3 is equal to y. Then tan y is equal to minus square root 3 is equal to minus tan pi by 3 is equal to tan minus pi by 3. We know that the range of the principal value branch of tan inverse is minus pi by 2, pi by 2, and tan minus pi by 3 is minus square root 3. Therefore, the principal value of tan inverse of square root 3 is minus pi by 3. Properties 1. Let's now learn about properties of inverse trigonometric functions. Sine inverse 1 by x is equal to cosec inverse x. X is greater than or equal to 1 or x is less than or equal to minus 1. Cos inverse 1 by x is equal to sec inverse x. X is greater than or equal to 1 or x is less than or equal to minus 1. Tan inverse 1 by x is equal to cot inverse x. X is greater than 0. Properties 2. Sine inverse minus x is equal to minus sine inverse x. X belongs to minus 1, 1. Tan inverse minus x is equal to minus tan inverse x. X belongs to R. Cosec inverse minus x is equal to minus cosec inverse x. Modulus of x is greater than or equal to 1. Cos inverse minus x is equal to pi minus cos inverse x. X belongs to minus 1, 1. sec inverse minus x is equal to pi minus sec inverse x modulus of x greater than or equal to 1. Cot inverse minus x is equal to pi minus cot inverse x, x belongs to 1. Properties 3. Sin inverse x plus cos inverse x is equal to pi by 2, x belongs to minus 1, 1. Tan inverse x plus cot inverse x is equal to pi by 2, x belongs to R. Cosec inverse x plus sec inverse x is equal to pi by 2, modulus of x is greater than or equal to 1. Tan inverse x plus tan inverse y is equal to tan inverse x plus y by 1 minus xy, xy is less than 1. Tan inverse x minus tan inverse y is equal to tan inverse x minus y by 1 plus xy, xy is greater than minus 1. 2 tan inverse x is equal to tan inverse 2x plus 1 minus x square, modulus of x is less than 1. 2 tan inverse x is equal to sin inverse 2x by 1 plus x square, modulus of x is less than or equal to 1. 2 tan inverse x is equal to cos inverse 1 minus x square by 1 plus x square, x is greater than or equal to 0. 2 tan inverse x is equal to tan inverse 2x by 1 minus x square, minus 1 is less than x is less than 1. Proof of properties 1. Let's prove some of the identities. First, sin inverse minus x is equal to minus sin inverse x. Proof. Let sin inverse minus x is equal to y is equal to 0. Hence, minus x is equal to sin y. Or x is equal to minus sin y is equal to sin minus y. Hence, x is equal to sin minus y. It implies that sin inverse x is equal to minus y, or y is equal to minus sin inverse x. Similarly, tan and cosec can also be proved. Cos inverse minus x is equal to pi minus cos inverse x. Second, sin inverse x plus cos inverse x is equal to pi by 2. Proof. Let sin inverse x is equal to y. Hence, x is equal to sin y is equal to cos pi by 2 minus y. Hence, cos inverse x is equal to pi by 2 minus y, or cos inverse x pi by 2 minus sin inverse x. Hence, sin inverse x plus cos inverse x is equal to pi by 2. Similarly, the other two parts can also be proved. Proof of properties 2. 2 tan inverse x is equal to sin inverse 2x by 1 plus x square is equal to cos inverse 1 minus x square by 1 plus x square is equal to tan inverse 2x by 1 minus x square. Proof. Let tan inverse x is equal to y, then x is equal to tan y. Now, we know that sin 2y is equal to 2 tan y by 1 plus tan square y. It implies that 2y is equal to sin inverse 2 tan y by 1 plus tan square y. Cos 2y is equal to 1 minus tan square y by 1 plus tan square y. It implies that 2y is equal to cos inverse 1 minus tan square y by 1 plus tan square y. And tan 2y is equal to 2 tan y by 1 minus tan square y. It implies that 2y is equal to tan inverse 2 tan y by 1 minus tan square y. Hence, 2y is equal to sin inverse 2 tan y by 1 plus tan square y, which is equal to cos inverse 1 minus tan square y by 1 plus tan square y is equal to tan inverse 2 tan y by 1 minus tan square y. Hence 2 tan inverse x is equal to sin inverse 2x by 1 plus x square is equal to cos inverse 1 minus x square by 1 plus x square is equal to tan inverse 2x by 1 minus x square. Example. Prove that 3 cos inverse x is equal to cos inverse 4x cube minus 3x. X belongs to 1 by 2, 1. Solution. To prove 3 cos inverse x is equal to cos inverse 4x cube minus 3x. X belongs to 1 by 2, 1. Let x is equal to cos theta, then cos inverse x is equal to theta. We have right hand side is equal to cos inverse 4x cube minus 3x is equal to cos inverse 4 cos cube theta minus 3 cos theta is equal to cos inverse cos 3 theta equal to 3 theta equal to 3 cos inverse x, which is equal to left hand side. Hence 3 cos inverse x is equal to cos inverse 4x cube minus 3x. X belongs to 1 by 2, 1. Did you know? Sin inverse x should not be confused with sin x inverse. In fact, sin x inverse is equal to 1 by sin x, and similarly for other trigonometric functions. Whenever no branch of inverse trigonometric functions is mentioned, we mean the principal value branch of that function. Summary. Let us summarize what we have learnt. The value of an inverse trigonometric function which lies in its principal value branch is called the principal value of that inverse trigonometric function. For suitable values of domain, we have the following formulas. For suitable values of domain, we have the following formulas.